Have you ever wondered how different computer programs, even those running on separate machines across the internet, manage to communicate and share information with each other seamlessly? It is a fundamental capability that underpins almost all modern software. The core principles of sockets for networked interprocess communication, or IPC, revolve around creating standardized endpoints for data exchange, enabling consistent communication across networks, and abstracting away the complex details of underlying network protocols. At its heart, a socket serves as a software abstraction layer. Instead of requiring programmers to directly manipulate raw network hardware or wrestle with the intricacies of various communication protocols, sockets provide a consistent, high-level interface. This abstraction offers a well-defined and predictable mechanism for processes to send and receive data, regardless of whether they resided on the same computer or are separated by vast geographical distances. This communication often follows a client-server model. A server creates a listening socket, patiently waiting for incoming connection requests. A client then initiates a connection to that server socket. This structure supports two primary modes of operation: connection-oriented sockets, typically using the Transmission Control Protocol, or TCP, for reliable, ordered data streams, and connectionless sockets, often using the User Datagram Protocol, or UDP, for faster but potentially less reliable packet delivery. For developers, understanding these principles translates into practical steps. It means consciously choosing the appropriate socket type for a given communication need, such as stream sockets for applications requiring guaranteed data delivery, or datagram sockets for real-time applications where speed is paramount. The interaction then involves a sequence of operations like creating the socket, binding it to a specific network address and port, listening for incoming connections if it is a server, connecting to a remote address if it is a client, and finally, sending and receiving the actual data. A key element facilitating this widespread communication is the Berkeley Sockets Application Programming Interface, or API. This API has become a de facto standard across virtually all operating systems. Its pervasive adoption means that a network program developed using sockets on one system can often be adapted to run on another with minimal modifications, greatly enhancing software interoperability and reducing development overhead. Ultimately, grasping these foundational principles means appreciating that sockets provide a robust, standardized, and remarkably flexible framework for building sophisticated distributed applications. It empowers you to architect systems where diverse components, irrespective of their physical location, can reliably interact and exchange information, which is an absolutely critical capability for virtually all contemporary software designs and troubleshooting endeavors.
If this helps you fix faster, like, subscribe, and keep debugging with us.